The three parts of the talk are in the title. That's the summary. Chaos, well, we heard about it already this morning. There's an old English dictionary which defines chaos as a confused heap of mingle-mangle. Okay. Now, I want to tell you one thing about it, which is that Newtonian physics is not deterministic. Newtonian mathematics is deterministic. I want to explain the difference. Now, if you have isolated objects with forces between them, the outcome is indeed uniquely determined by the initial state. And we know, we heard this morning, any initial uncertainty can grow slowly. For example, if you have planets over short time scales, that's regular motion, or quickly, for example, pinball machines, that's chaotic motion. Now, here's a little toy, you may have seen it. It's my counterpart of what Chris showed us this morning, a conical pendulum, which may or may not have little magnets on the bottom. If it doesn't, the motion is regular. It's motion under gravity, this rosette pattern. If you have magnets there repelling, the competition between their repulsion and gravity gives you chaos. Well, we heard enough about that this morning. But still, is it determined in principle? Well, mathematically, yes, but physically not, because isolation would violate physics. Why? Well, you can't screen out gravity. So claiming perfect isolation isn't Newtonian physics. Okay, this has consequences. Here you have molecules in a gas in a box. They bounce around under their mutual influence. I'm thinking of them classically. Now, of course, there are perturbations from outside. What's the weakest perturbation I can think of? Take the gravity from an electron at the observable limit of the universe, 10 to the 10 light years away. Well, you don't know where it is. Its gravity affects the molecules differently. As I say, you don't know where it is, and that introduces uncertainty, which is magnified by this convexity. And you can ask, after how many collisions is the emergent direction uncertain by 90 degrees? You can call that loss of predictability. Well, the answer is about 50. It takes place in a nanosecond or so. So incredible sensitivity to initial conditions. By the way, if you're a billiards player, your gravity around the billiard table would make the billiard ball direction uncertain after about 10 collisions. No billiards player can reliably plan a shot of more than about 2 collisions. Well, is it possible? In principle, we heard about Laplace. If we could know where every particle in the universe is? Well, the answer is no, because that would include the particles in the computers doing our calculations or in our heads, and that gives rise to contradictions. So even in principle, this Laplace's idea doesn't hold true in Newtonian mechanics when you have chaos. So classical physics is not deterministic. Classical mathematics, of course, is. Right, quantum. The quantum world is utterly different in many ways. You have discrete energy levels for an isolated system. It's indeterministic, but in a different way from what I've just described. The unpredictability of radioactive decay doesn't seem to originate in influences from distant objects. You have the wave nature of matter. You have a result which is, in an isolated system, there is no chaos. I can't describe that to you, it would take too long, but it's to do with the fact there are discrete energy levels which inhibit the sensitivity with which initial quantum states would evolve. And that's why I always call the subject quantum chaology, not quantum chaos. Chaology meaning what are the reflections of classical chaos in a corresponding quantum system. It's not chaos itself. Chaology, if you look in the Big Oxford Dictionary, with rare words, they list the number of times that they've found occurrences of those words, like rare 3. Well, chaology is rare 0. And I asked the creator of the online version of the Oxford English Dictionary what that means, and he said it means we only found it in earlier dictionaries. Okay. Now, there's a new fundamental constant, of course, Planck's constant, usually written like this. It's rather small in everyday units. The units are units of angular momentum, 10 to the minus, 10 to the minus, I didn't put it there, 10 to the minus 30 something, sorry. Anyway, very tiny. Now, we have a correspondence principle. Quantum mechanics must reduce to classical mechanics in the limit when Planck's constant is negligible. 0, we call it, negligible compared to other quantities of the same type. Well, that's correct, but it conceals a lot more than it reveals, for a reason which is my central point. I'll get to it. It's an example of something more general, how different levels of description are related to each other. Statistical mechanics of matter reduces to thermodynamics in the limit of many. That's a particle number. Philip Anderson beautifully wrote about this. More is different. All kinds of difficulties arise with that limit. In fluids, viscous flow reduces to slippery flow as the viscosity goes to 0. Many problems still not understood about that. It involves turbulence. In light, wave optics reduces to ray optics as the wavelength goes to 0. And of course, we have this example of quantum mechanics. Now, there are two ways of thinking about this difficulty of taking limits, and they're both oversimplified. One is, are these incompatible descriptions? I'm adapting a phrase of S. Stephen Jay Gould. Are they non-overlapping magisteria, not to be mixed? Or, in a beautiful Old English word used by E.O. Wilson, should we seek consilience between these different levels? I'm more sympathetic with the second, but they both have their place. Now, common to these correspondences is that they involve mathematical limits. Now, in almost every case, discordance is associated with the fact that these limits are mathematically singular. It's a fundamental mathematical phenomenon central to this understanding of differences between levels. Now, a singular limit needs explanation, and I'm going to give you a very simple example. Bite into an apple. If you see a maggot, you're unhappy. If you see half a maggot, you're even more unhappy. A quarter of a maggot, more unhappy still. Take the limit. If you see no maggot at all, you should be infinitely unhappy. But of course you're not. It's a singular limit. The limit of smaller and smaller maggot fractions, infinite unhappiness, is different and discordant with the limit of no maggot at all. You're happy. You continue eating the apple. So common language, simple example of a singular limit. Now, this perspective enables two insights which are qualitatively different. One is reassurance, to show that the old theory emerges from the deeper one, usually not straightforwardly, but you know it must happen. When you program a spacecraft to go to the moon, you don't write the Schrödinger equation and treat the spacecraft as a wave packet. Of course you don't need to do that. So you know that in some sense you will regain classicality, not trivial. And the other is there's a creative aspect, because it leads you to identify qualitatively new phenomena inhabiting the borderlands between the two levels. Now let's look at the reassurance, quantum to classical. The simplest possible case, take two oppositely directed beams of particles or beams of light. Here they are. Now, when they overlap, the intensity is doubled. Two flashlights are twice as bright as one. The mathematics is 1 + 1 = 2. You may know that formula. Now, but of course, if you have waves, which deep down you know that you do have them, that's different. The intensity is the square of an interference amplitude. 1 + 1 is not equal to 2. intensity can be anything between 0 and 4. Now, the limit is when the wavelength goes to 0. It's the same in quantum mechanics. So the oscillation gets faster and faster when it goes to 0, and the limit is very singular, anything between 0 and 4. Well, you know that beyond a certain point, the wavelength is too small to resolve, or the delicate coherence leading to this nice pattern is destroyed by external influences, and you see only the average. Well, the average is in fact 2. So 1 plus 1 equals 2 is restored by something we call decoherence. Now, I'm not being pretentious when I say that 1 plus 1 is not equal to 2. As pure mathematics, it's of course a very simple formula. Even though, if you know Russell and Whitehead's Principia Mathematica, 1 plus 1 equals 2 appears only halfway through volume 2 as the first non-trivial example of their mathematics. But still, it's as pure mathematics, it's simple. But this is applied mathematics, and you have to understand with any piece of mathematics, if you want to talk about it in connection with the world, whether it actually corresponds. You know, 2 people get together, produce a child. 1 plus 1 equals 3. 2 raindrops come down the windscreen of your car and coalesce. 1 plus 1 equals 1. You have to know when it applies. It doesn't apply to wave intensities unless you introduce something external like decoherence. But still, you have reassurance. Now, this sensitivity to decoherence becomes more and more exquisite if you approach the classical limit in a case where there's classical chaos. And here's an example. Saturn's satellite Hyperion. It's a few hundred kilometers across, this potato-shaped rock. It tumbles chaotically under the influence of the gravity of Saturn and some of its satellites. It's roughly a period of about 13 days. Its uncertainty doubling time is about 100 days. Now, think of this as a quantum object. It has a quantum rotator, about 10 to the 60 Plancks in its angular momentum, okay? And if it were isolated, any uncertainty would grow and get increasingly complicated in the relevant space until it reaches a scale of Planck's constant, and then quantum mechanics can't see it anymore. And that's, after that, Hyperion would reveal its quantum nature, and the way it would happen, so I don't have time to explain it, but it's energy driven by these external, well-determined gravity from satellites from Saturn would no longer increase. That has a name. It's called the quantum suppression of classical chaos. It's seen in molecular experiments. It exists. Well, when would that happen? Well, after about 40 years. It's a remarkably short time because of this chaos and uncertainty, and it's obviously nonsense. You don't look at Hyperion for 40 years and see its chaos suddenly stop, or even gradually stop. The reason, of course, is that this suppression of chaos is an effect of extreme coherence requiring strict isolation. Of course, it isn't isolated. A single visible photon from the sun, whose re-emission enables us to see it, has an energy of about 10 to the minus 19 joules. That's tiny compared with Hyperion's rotation energy, which is about 10 to the plus 19 joules, but it's huge compared to the energy separation of the energy levels of these different angular momentum quanta in Hyperion, which are about 10 to the minus 39 joules. Well, that means that the stream of photons from the sun, their uncontrolled external influence, completely destroys the quantum coherence in about 10 to the minus 53 seconds. Okay, so decoherence suppresses the quantum suppression of classical chaos and restores classicality, and that's why astronomers don't use quantum mechanics when they're describing the motion of Hyperion. So that's the reassurance aspect. Right.